All right, well, good afternoon. Good to see everybody. So today we're going to learn yet another method for dealing with these linear second order. So last time I showed you reduction of order, which does exactly what it sounds like it does. It takes it from a second order to a first order. But the catch is that we actually need to know one of the solutions to the homogeneous. But we often know one of them, and or we can find one of them pretty easily. And that kind of complements the undetermined coefficients method, which if you think about that one, that worked really well when the non-homogeneous part was nice, right? When it was exponential, polynomial, trig, something like that. So what we're going to do today, this new method, variation of parameters, it's going to allow us to take care of ones whose forcing function whose non-homogeneous part may not be nice. What if it's natural log? What if it's tangent? What if it's something that's not an easy form to try to guess to find the particular? Well, that's what variation of parameters are going to do. You will see the drawbacks of it, but it is kind of nice. But before we get there, just want to open it up to you guys. Any homework questions you'd like to look at? I imagine there might be some because homework's due tonight.
Yeah. Could we do 5.316?
5.3, number 16. All right, that's on the list. Any others?
Could you do 29 on 5.2?
5 to 29. All right, got that too. All right, well, how about we go find those? So go ahead and share my screen here. All right, so let's look at 5.2, number 29. We'll look at that one first here. So it says prove that if the characteristic equation of this guy, ay double prime plus by prime plus cy equals 0, has a repeated negative root or two roots with negative real parts, then every solution of A approaches 0 as x goes to infinity. All right, well, I think the best way to do this is just to kind of slug her out. Right? So this was what, number 29? Okay, so let's look at what case number one is. Case number one was a repeated negative root. And then case number two, I'll probably need more space. Case number two is two negative roots. All right. So let's actually start with the two negative roots. So we go and we solve, we get two roots, and think about what our solution looks like. It's C1 e to the, and I'll just call it minus R1t plus C2 e to the minus R2t. So minus R1 and minus R2 are our two roots. All right, so what's the limit as t goes to infinity of this?
Yeah, it's 0.
Okay, so we're going to get 0 for both of those pieces, regardless of what C1 is. I mean, C1 could be a bajillion. We'll make up big words here. It could be a bajillion and it doesn't matter, because eventually this e to the minus RT is going to get so small that it's going to carry on down to 0. So the two negative roots is a pretty easy one to see. Okay, so let's think about the repeated negative root. All right, so that means we're going to get C1 e to the minus RT. And then what's our other function? When we get a repeated root, what do we do?
We add a t in front.
Good. So we'll make it a t e to the minus RT. And so it's the same question as before. What's the limit as t goes to infinity? Now, the first one's pretty easy. That's clearly 0 for the same reason that these guys were 0. But what about this one? Well, to actually find that limit, let's go back to L'Hopital's rule. We're doing the limit as t goes to infinity of t over e to the RT, which is infinity over infinity. So we'll do a good old L'Hopital. So L'Hopital, we take a derivative of the top and the bottom separately. And we take our limit. Well, again, there's going to be 1 over something very, 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 very big, which gives us a 0. All right, so there you go. We have shown, let's actually just go double check what it said we needed to do. So we prove if the characteristic equation has a repeated negative root or 2 roots with negative real parts. Oh, negative real parts. We're not quite done. It's a good thing I went back and looked at it. Because that means there's a third case. What's case 3? We're going to have these, right? We could have complex. We're just told that lambda is less than 0. So in that situation, what does our solution look like?
Like e to the lambda t times cosine of omega I or t.
Yep.
Plus
Okay, good. Thanks, Victor. So we have e to the lambda t times cosine of omega t plus sine of omega t. All right, well, again, what about the limit as t goes to infinity? Now, the cosine and the sine bit, there is no limit on those, right? They're just going to keep bouncing around. But the e to the lambda t, since lambda is negative, that's going to equal 0 times whatever cosine sine business. And I know that that is finite. It's never going to be more than 2, right? It'll never be more than 2 for sure. So that also equals 0. So now I think we're good. We had the repeated and then the negative real parts. Okay, well, it could just be 2 negative real numbers, boom, or 2 complex numbers with imaginary, or sorry, with negative real parts. And that drives that exponential piece. So that's why this ends up being the case, because all of them, if you look at every single one of them, they've got an exponential piece. And every one of those exponential pieces has a negative exponent, which means as we go towards infinity, they're going to die out. So just think about what all the different graphs are going to look like. The one that's just the sum of the exponentials, it's pretty much just going to look like an exponential that goes down. The one that's an exponential plus the linear piece, it probably goes up for a bit and then goes down. And then the one with the sine and the cosine is going to be one that oscillates, but the amplitude of the oscillation dies out. Like case 3 would be what you see with like a spring. When you take a mass on a spring, you pull it down and you let it go. You know, and back in the day, we would just say, well, it goes forever. But now, if we add in the air friction, we'd see that it does die out, and it's going to follow something like that. Hey, guess what? We're going to do springs as an application in a little bit. That's another cool place where differential equations come in. All right, so I think we're good for 29, right? Is that good for you, Bradley?
Yeah, definitely.
And my advice always with these proof things is break them into the cases and always just try to think about, is there some case that I'm not seeing? Just to make sure you've got all your bases covered, as they say. All right, so let's go back to the book and go find the other one. Let's see, it's 5.3, number 16. I love having the little table of contents thing here. Makes life so much easier. Okay, so for 16, we're trying to find a particular solution and then find the general solution. So the particular, remember, is the little y sub p. It's a function, it's a solution to the non-homogeneous that then we add to linear combination of the fundamental set of solutions to the homogeneous that gives us the general solution. All right, well, let me write this one down and then we'll go to the whiteboard. All right. So I'm going to clear all that stuff and we'll start fresh. All right, so we had y double prime plus 5y prime minus 6y equals 6e to the 3x. Okay, so my suggestion is always start with the homogeneous. You're going to need it anyway, so you might as well find them first. All right, so constant coefficients. So we get to make our polynomial. And this one factors to r plus 6, r minus 1. Okay, so that gives me y1 is e to the minus 6x. And y2 is e to the plus x. All right, so there's a fundamental set of solutions for the first, or for the homogeneous part. All right, so hopefully by this point, you guys are getting pretty good with this. It's pretty quick. It's not that hard. So now let's go to the y particular. So for y particular, we're going to make a guess. Since I've got an exponential form here, I'm going to guess an exponential form of the same type. But I am going to allow it to have some other multiple in front of it. And the goal is to find out what that a is that would make this true. So I want to real quick just check this e to the 3x against my fundamental set. It's not in there. They're different exponentials than e to the 3x, so we're good to go there. All right, so any questions at this point? We good to go? All right, well, let's get our derivatives and our second derivative. So the first derivative is going to be 3a e to the 3x, and then the second derivative is going to be 9a e to the 3x. Okay, so Jesus, that's a really good question. If they are the same, so like let's say instead of being 6e to the 3x, it was 6e to the x, and you go, okay, that's the same. Does anybody remember what we have to do? What do we
We need
change
to
in?
use the integrating factor.
Okay, so we put in an integrating factor, which is going to be a power of x out front, and it's going to be whatever power we need for the number of times that shows up as a root. So since this one was just e to the x, we would have to use x e to the x. If it had shown up twice, if this had factored, let's say, to r equal 1 and r equal 1, then we would have needed an x squared e to the x. So if they're the same, if you're non-homogeneous, if your forcing piece is identical to one of the fundamental set, you just need to multiply it by x or t. And I just realized I wrote x
The
there.
double prime shouldn't have an x.
Yeah, I just saw that. All right, so now let's put these into the differential equation. So we get 9 a e to the 3x plus 15 a e to the 3x minus 6a e to the 3x. We want that to equal 6 e to the 3x. So we can add our coefficients together. We get 18a, if I did the math right. Although my arithmetic has been sketchy lately.
I got 20 a e to the 3x.
Yeah.
Wait, no, I'm sorry, I'm wrong. For some reason, I never mind.
You carried a one that wasn't there.
Yeah.
Okay, that's all good. No, I don't mind you. I don't mind you checking me because I would much rather catch it earlier. All right, so now we know what our particular solution is. So this is a function that satisfies the original differential equation. And that's all they're saying. That's all you ever need if they're just saying find a particular solution, is just find a solution. All right, but now we get to put this all together to get our answer. So our answer is going to be always of the form yp plus c1y1 plus c2y2. So we're going to take our particular solution we just found, 1/3 e to the 3x, and then add to it linear combinations of our fundamental set. And there's your general solution to that differential equation.
What was the stuff at the top of the that problem segment talking about with like alpha, and it said like if blah 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 is constants, then use it.
I don't know. Let's
by
go look
that.
at it. I didn't actually read it. I just jumped in and did the question. So let me see.
Yeah, because that's what got me all confused. Was I got caught up with that whole thing, and I was a little bit confused as to how to proceed.
Okay, so it says if A, B, and C and alpha are constants. Okay. So, excuse me, for us, A, B, and C are 1, 5, and -6. And then alpha is 3. That guy right there. And I think what they did here, they just did it generically. Because if you look at what this has here, right, it has A alpha squared plus B alpha plus C. So think about what we had when we combined everything. So that A alpha squared is 9 times 1, so 9. plus 5 times 3, so 9 plus 15, minus 6. Those were the coefficients we had on A. And so what we knew then is to make that equal 6, we need to get our 1/3. So I think this is really just kind of showing you like a shortcut to the what you're going to get when you do the steps. So like for 17, if you wanted to be fast about it, you'd go 1 times 2 squared is 4. 4 times 2 is 8. So 4 minus 8 is -4. Plus 5 is 1. So you're going to get 1a equals 1 or a equals 1. So our function is going to be e to the 2x. 1 e to the 2x. So I think that's all that they were saying there.
Okay.
I just dive in and do it because I'm not a formula memorizer. Like this does me no good. This piece right here, like I don't care about that. I'm not going to memorize that ever in a million years. I just think about what form I need and then differentiate them.
So one thing I was thinking about through this section is at least I can't quite see it, but it's surprising to me that we're not integrating like explicitly.
Yeah, kind of cool, huh?
Yeah. I mean,
yeah, we're solving differential equations without actually integrating. But that's because it's a nice form, right? Like think about the one we just did where what we were looking for was something of the form e to the 3x. That's a super nice form. No big deal. We already know what kind of function we're looking for. And so you do kind of get fooled here a bit by going, oh, there's no integration. We're going to see that that is going to come into play here. And or when we do variation of parameters. But it also happened with reduction of order, right? Think about when we did reduction of order last time, when we multiplied by the u and then all that. We always ended up with a u prime equals, or I guess we called it like w prime, or w equals u prime. And so we had to integrate there. So the only reason we don't have to do any integration in this section, in the undetermined coefficient section, is because the forms are nice. We know what to expect, right? Like you already know what kind of function is going to give you e to the 3x. It's going to be e to the 3x. But if that had been equal to the secant of x, no clue. No clue what kind of function might lead me there. And that will make us have to integrate. But that is an interesting observation for sure, Bradley, that sometimes you can solve these things without any integration whatsoever. But these are pretty simple, right? I mean, think about the equations we're seeing with the constant coefficients and everything. They're pretty basic, which means out there in the real world, they do show up from time to time, but usually they're a little bit gnarlier. So, but yeah, if you can guess a form, guess a form. It's way nicer to do undetermined coefficients sometimes. Or, well, it makes it just algebra, which nicer, that's depends who you are. So, all right, so cool. Any other homework questions, or are we good to move on? All right, well, hearing nothing, we'll go ahead and move on. All right, so now let's talk about times when it's not so nice. What are some other methods that we can use? All that good stuff. So let me just present this to you as an example of a differential equation that is pretty similar to what we've been doing. All right, I mean, it actually is quite similar. However, it's got some, yeah, issues attached to it. So we're going to go with y double prime plus 4y equals 3 cosecant of x. Well, I'll make it a t. I know the book uses x. I use t. I prefer t. That's the physicist in me, because everything is with respect to time pretty much in physics. All right, so let's just look at this one. And let's think about what our process would be. So if we classify it, you just start with the classification of this thing. We've got second order, linear, non-homogeneous, but constant coefficients. Okay. So what that tells us then is we would want to do what we normally do. We're going to find the solutions to the homogeneous. Then we'll use that and add it to a particular solution and go from there. So we would probably start the same old way that we've done a billion times. We're going to get r squared plus 4r equals 0. Right? Notice that there is no 4r. Should just be 4. There actually is no r term here because there's no y prime. So this gives us complex numbers of plus or minus 2i. But from that, we can get our solutions. Since they're complex, we're going to get e to the 0t times a cosine of 2t plus b sine of 2t. Should have called those C1 and C2. Right, and then of course e to the 0t just goes away. So in terms of our fundamental set, we've got this. So we're cruising, right? We're almost done. The only thing we need is a y particular. Only.
I have a quick question for you
Sure.
before we go farther. Would it
Yeah.
be practical to use a trig identity on something like this?
You mean like a double angle identity or something?
Exactly, yeah, double angle identity to maybe combine it.
Probably not. Because if you think about the double angle identities for both of those, they don't have a lot in common. The cosine, well, the sine is 2 sine t cosine t. And then the cosine, you've got the 3 different forms, but it's like cosine squared minus sine squared, 2 cosine squared minus 1, 1 minus 2 sine squared. None of those are really terribly useful in terms of combining. So I would probably leave them like this. However, if you are actually doing this where you get a particular solution or a particular solution to the original differential equation, so you got an initial value problem. When you have sines and cosines that you're adding together, you usually do want to combine them because you can combine them into one. I don't know if you remember doing that in physics, but like whenever you have 2 waves added together, you can actually combine them into one. So in that situation, I would put them together, but otherwise, I would just leave them like this. But that's a blanket statement. Obviously, there are going to be times where identities might be useful. All right, so I'm going to put a little h on that just so that we recognize that that was homogeneous. The homogeneous solution. Okay, so now we got to get to the particular. So if you kind of continue the thought process of what we did before, you now look over here and you go, okay, I've got a 3 cosecant of t. So before we just made a guess. Well, what kind of function can you think possibly maybe would give you a cosecant when you take its second derivative and add it to 4 times itself?
The natural log of sine.
Okay, so we do know that when you differentiate, you can differentiate to get cosecant, and that is the natural log of sine. Okay, but if we went with y is a natural log of sine, think about that. It's going to show up as 4 times the natural log of sine plus some other stuff. Is that natural log of sine going to go away?
No.
We're not going to get a negative natural log of sine that's going to cancel with their second derivative. So it's like, okay, that's not going to work. You think about other things that give you cosecant, cotangents, cosecants. But start thinking about those derivatives, right? Cotangent gives you a cosecant squared, which then when you differentiate again, now we have to use power rule and product rule. And the same thing with if we start with cosecant, it's not obvious. So just think about the very small tweak we did. Had this been 3t, no problem. 3 cosine of t, no problem. 3e to the t cosine of t, no problem. Right? Anything like that, we already know how to tackle with undetermined coefficients. So this is exactly the same, or the type of problem that leads us to, we need another trick. We need something else. And that's variation of parameters. So what we're going to do is kind of walk through variation of parameters with this problem. And then we'll kind of get it back and generalize it. All right. So here's what we're going to do. We're still going to make a guess. We're going to make a guess for our particular form, because why not? I mean, we make guesses for everything all the time anyway. But here's what I'm going to do. I'm going to do the whole integrating factor thing. But I'm going to make it so that I've got 2 integrating factors. So this is very much like reduction of order. Remember when we did reduction of order, you had to have a solution to the homogeneous. Well, in this case, we actually have both solutions, or we have 2 functions that form the entire fundamental set. So I'm going to be looking for guys of this form. Now, here's the beautiful thing. No matter what that function is, we're going to be able to split it apart like this. You can always write it as a multiple of these 2, right? Like think about it. Here's a generic, let's just say it was f of t. We could make that 1 times cosine of 2t plus f of t over sine of 2t times sine of 2t, right? Like if I were to distribute this all out, -1, this is going to give me f of t. So no matter what function we've got, we can always write it as a product or sum of products of these guys with other functions.
Why did you choose the cosine and sine of 2c?
Because they were my fundamental set.
What about the e to the e to the t?
That's actually e to the 0, because there was no real part here.
Oh, I see. I put 1 for that value, but I guess it wouldn't be a 1.
Right.
Got it.
All right. So we can always do this. It's just going to be a question of what are u1 and u2 equal to. All right, so sorry, I'm getting a little stiff sitting here. How are we going to do this? Well, think about what we've done every single time we've ever had one of these scenarios where we've got an integrating factor. We just dove in and started doing derivatives, right? So let's do that here. If y has this form, then yp prime is going to be u1 prime times cosine of 2t minus 2u1 sine of 2t plus u2 prime sine of 2t plus 2u2 cosine of 2t. All right, so that's what y prime looks like. Now, before I go to y double prime, we're going to pull a trick. And this is going to be one of those things where you're going to go, what? And I'm going to say, well, yeah, we do it because it works. Is a quote unquote miracle step. I'm going to put conditions on u1 and u2. I'm going to put conditions. And in fact, I'm going to put this specific condition. I'm going to want the u1 prime times cosine of 2t, so this piece, and the u2 prime sine of 2t, that piece. I'm going to put on the condition that they equal 0. So there's nothing about this differential equation that suggested to do this or anything. I'm just doing it because I want to. So we're going to add this restriction. Okay, now it's definitely at this point that students in this class go, what the what? How can we just randomly, arbitrarily decide I'm going to add in this restriction? It feels wrong, right? Like, think about all the times that you're ever doing stuff and we tell you when you're proving things, you can only use what was given, don't make stuff up, blah, blah, blah. And here I am making stuff up. Okay, well, here's the deal. Think about U1 and U2. Think of this as like system of equations kind of thing. If I gave you two variables, just two random variables, if I apply one condition to them, that doesn't actually tell you anything about the variables, right? Like what if I told you A plus B is equal to 5? What does that make A and B?
Nothing special.
I mean, two numbers that add up to 5, okay. But then I still have room to give you another condition if I want to specify A and B, right? I can say, okay, well, A plus B add up to 5, but the difference in them is 3. And now all of a sudden, okay, that second restriction brings me to my specific values. So same kind of things happening here with U1 and U2. I actually have the ability to put two conditions on them and still be able to find them. If I added a third condition, it's possible that I get a system that doesn't have a solution, right? But I can put 2 on all I want. And this is going to be one of those 2.
And you can do this kind of randomly?
Yeah, I can do it however I want, as long as I limit myself to 2.
Okay.
Okay. So this is one of those 2. Now it turns up I've actually used up all of my restrictions. because there's another restriction on U1 and U2. You guys see where it is?
Probably the 3 cosecant of t.
This bit here?
Yeah.
No, not really.
The C1 and C2s, they
Down here?
can't be the same. Yeah.
Okay, but remember that this has nothing to do with the U's. I'm talking about restrictions on U's. It turns out it's this first line. This is also a restriction, right? U1 and U2 are not just any old random functions.
They're differentiable functions.
Well, they have to be differential, but I also needed them so that they're going to form my particular solution. Okay, so just by making that statement, by saying, I want my particular solution to be made up of these U1 and U2 of this form, that's a restriction on U1 and U2, right? Because now U1 and U2 can't just be any old random functions. They're gonna have to make it so that this is a solution to the differential equation. So that's a restriction. So that was restriction number 1. I had one more that I could use because it's a 2-function deal. And that's where I'm going to put this guy in. All right, so we're going to add in that restriction. And I know that you're probably still going, yeah, okay, whatever. So think about what that makes this derivative look like then. It's now minus 2u1 sine of t plus 2u2 cosine of 2t. Now let's find the second derivative. So it's going to be minus 2u1 prime sine of 2t no, not plus. Minus 4 u1 cosine of 2t plus 2u2 prime cosine of 2t minus 4u2 sine of 2t. All right. So now let's make use of our differential equation. We're going to take that, put that into the y double prime. We're going to take this, put it in right there. And so when we bring that back, and we've got now our, what we get when we plug this stuff in, notice with this 4, we get 4u1 cosine 2t, which is going to cancel with this minus 4u1. We're going to get 4u2 sine of 2t, which is going to cancel minus 4. So we're left with minus 2u1 prime sine of 2t plus 2u2 prime cosine of 2t. And that's going to have to equal 3 cosecant of t. So if you look at this, you just kind of see what's going on here. This tells us something about u1 and u2. Its derivatives have to be such that when I put it into this, I get 3 cosecant of 2t. All right. Well, let me draw your attention. I mean, we already have that, so put a little box around that because that's going to be important. But let me redraw your attention to the restriction that we placed on it. And notice that that's also a restriction on the derivatives. Well, check it out. That's a system of equations. two equations, two unknowns, u1 prime, u2 prime. Not only that, I can write this as a matrix equation. I'm going to have cosine of 2t, sine of 2t, minus 2 sine of 2t, 2 cosine of 2t, times u1 prime, u2 prime, and that needs to equal 0, 3 cosecant t.
Is this a Wronskian?
Wait, what? Yeah, good eyes. Check it out. Remember when we built the Wronskian matrix with our solutions? Here were our solutions, cosine 2t and sine 2t. There they are. The next row is their derivatives. All right, so the Wronskian matrix is back. All right, well, regardless, this now gives us a way to solve for this, right? I'm going to call that matrix W for Wronskian. So now what we need is just the inverse. So we're going to get that u1 prime, u2 prime is going to equal the inverse of the Wronskian times 0, 3 cosecant t. All right, am I going to be able to find the inverse of that matrix? That's a question we definitely should be asking ourselves. Because without it, we're not going to be able to get a solution.
Yeah, the determinant is not 0.
It's definitely not 0 because those are a fundamental set, right? We talked about that before. Since they're, and if we go back to linear algebra language, because they're linearly independent, that matrix is going to have a non-zero determinant. All right, so, I mean, check it out. We've got the process now to find this. We just have to get the inverse of this matrix and multiply it by the 0, 3 cosecant of t. And that'll get us our u1 prime and our u2 prime. Okay, so I'm going to spare us a little bit of time here. I'm just going to jump to what this ends up equaling, because you know how to find the inverse of this. I mean, Christ, it's just a 2 by 2 matrix. So in a worst case scenario, just go ahead and, you know, blitz through and find it. Yeah, it turns out that the determinant of this matrix is just 2. It's kind of nice. So when you do the whole like swap and do all that kind of stuff. Well, anyway, when you end up doing this multiplication, you end up with u1 prime equaling, the top here is going to be minus 3/2 sine of 2t cosecant of t. The 3 cosecant came from that piece, and then the minus 1/2 sine of 2t is the bit from the multiplication. And then the u2 prime, this one ends up being shoot, what was it? Oh, I didn't write that one down. Crap. All right, hold on. Let's just get the inverse real fast. The inverse isn't that bad. I just erase this. 3/2 cosine 2t cosecant. That sounds about right. I'm going to trust you on that, Ralph. Let's see if it ends up working out. So 3/2 cosine of 2t, cosecant t, swap, cut in half. Yep, I think you're right. I like it. Okay, so now since we know what u1 and u2 prime are, we can go ahead and figure out what u1 and u2 are. But this is where we're going to use our identities to help us out a little bit. Because sine of 2t, so check this out. So we've got u1 prime equals sine of 2t is 2 sine t cosine t. So the 2's cancel, and also the sine and the cosecant cancel. So you're left with, this is just minus 3 cosine of t. All right, and then if we do the same thing for u2 prime, you can actually simplify that a bit as well. I'm going to use the 1 minus 2 sine squared t bit for this cosine of 2t. Remember, there are 3 choices. I'm going to use this one. So this ends up being 3/2 cosecant t minus 3 sine t. All right, so here we go. So u1 is going to be the integral of the minus 3 cosine of t, which is minus 3 sine of t. And I'm going to put plus c1. And then u2 is going to be the integral of this piece, which is going to give us 3/2 natural log, oh wait, no, that's not, yeah, natural log of cosecant minus cotangent plus 3 cosine of t, but plus c2. All right, so by doing this, we were able to figure out u1 and u2. And just to kind of remind you the whole point of this, what were u1 and u2? What are we going to do with those?
Those are going to be multiplied to our original YP.
Okay, so they form our original YP, right? We get our YP is going to equal u1 times cosine of 2t. So we're going to get minus 3 sine t cosine of 2t. And since I can have any solution, I'm going to let my c1 equal 0, just to make life easy. And then we're going to add to that this other one times sine of 2t. And again, because it can be any, I'm just going to let it be that guy. All right, so that's where we are. So there's a particular solution. That is a function that when you plug it in here gives you a solution. And there's no way ever in a million, bajillion, gazillion years that you would have seen that. And I definitely don't mean that in any kind of a bad way, because I wouldn't have seen that. Because of the fact that this is not a nice form. And yet we were still able to get there by pulling this trick. So let's put it all together. Let's write out what our answer is then. Oh, this is one where I would definitely use some trig identities, by the way. Because see this piece here where it says 3 sine cosine. The other one has 3 cosine times sine. And the angles swap. That's a sine identity, a difference of angles for sine. If you look at sine of alpha minus beta, that gives you this thing. So it turns out, so this piece plus this piece, that actually just equals 3 sine of t, just by the way. So we're going to get 3 sine of t. I love trig. You get the quirkiest things that show up. Okay, so, and then that's the rest of that. And then we add on to that the homogeneous piece. So big exhale, sigh of relief. But there's our solution. Yeah. All right. So let's think like mathematicians for a second, because right now you're thinking like students, and that's okay because you are. But you're thinking like students. Oh my God, so many steps. This sucks. Which I get. Trust me, I get. But think like a mathematician. What does a mathematician say here? They say, damn straight, this worked. Let's generalize it so that I can do it every time, not just when it's cosecant of t, not just when it's these specific functions. Is there a way for me to take this method and just go, let's always do it this way? And the mathematicians went, yep, there totally is. So let's kind of break it down. And let's see if we can sort of build how we do this in general.
I
right.
have a quick question.
Yeah, go ahead. I was going to say before we do that, let me clear up anything on this one.
For your final answer, where it's natural log of cosecant of t minus cotangent of t, why is that multiplied by sine of 2t?
Because of there's distribution. I started doing this against my laptop and it didn't work.
I see it. Never mind.
Yeah, it's the distribution rate there.
Got it.
All right. Okay.
Is
So
there
yeah, go ahead.
Is the restriction always equals to 0?
All right. So that is a good question. Are we always going to use that restriction, or did that just work out with this guy? That is the restriction we're always going to use. We're always going to put that into place because that's going to help us like solve these things and deal with them.
See, I thought it was specifically 0 for that one as well because trig. There's a lot of zeros in trig.
There are a lot of zeros in trig. Let me show you. Let's go to a generic where we're just going to assume that we've got a y1 and a y2. And we're not going to care that they're cosine of 2t and sine of 2t, but we'll let them be whatever. And we'll also go with the generic what it's equal to. So the fact that there's a lot of trig here, I can see why that makes you start thinking, oh, we just got lucky because identities, blah, 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 whatnot. But let's break it down. Let's actually just try this generically and see if we want that same restriction. Turns out we are going to. See if we continue to get the Wronskian. We will. And then see what that leads to in terms of getting the solutions. Because it turns out that if we do it one time generically, most all this work that we had to do to get here, well, everything that's not on the page anymore that I've already erased, we're not going to need. So that's going to be a nice thing once we're there. So let me go ahead and clear this. And again, if you didn't catch something on here, feel free to go back to the video and watch it. But it's all gone now. All right, so let's go generic. Let's go 100% generic on this. And I'm not even gonna make it so that we have constant coefficients. Let's just write it in the super generic way that we've done before. All right, except I think the book calls that G and not F. Hold on a second. I think I'm trying to remember the book notation, but we're gonna go with G. Okay, so let's kind of break down what we did. So we started by finding Y1 and Y2 as a fundamental set. Okay, so those are going to be solutions to the homogeneous part. And then we went to the, let's make this a Y. Our Y particular was going to be some U1, Y1 plus U2, Y2. All right, so we'll go ahead and differentiate again. So let's think about our restriction. The restriction we did before was the piece that had the, with the cosine and the sine and all that. But let's think about what we really got rid of. We chose that restriction such that the parts with the U1 prime and U2 prime went away. So if you go back and you look at that previous example, the Y1 and Y2 were the cosine of 2t and sine of 2t. And those were the ones that we did set equal to 0. Now, why is it this restriction that we want? Well, think about what happens now when we differentiate again. If I didn't get rid of those pieces, now I'm going to get U1 double prime, and I'm going to get U2 double prime. And I don't want that. I mean, this is basically a reduction of order idea. I'm trying to make it so I don't have second derivatives anymore. And that's why that restriction is huge.
But it's okay with the fundamental set.
What do you mean by it's okay with the fundamental set?
Well, because if those go to 0, we're still going to get a Y1 double prime and a Y2 double prime.
Yeah.
Eventually.
Yeah. And that stuff's okay because it's going to end up being dealt with in here. But this is exactly the same restriction as we had done the other time. It's just with the generic Y1 and Y2. Okay, so now let's go the next step and let's see where this takes us. Okay, so if that stuff's gone, then Y prime, YP prime is just U1, Y1 prime plus U2, Y2 prime. Okay, so now let's take a second derivative. And so there are the double primes showing up, but on the y's. And again, let's take these and put them into the differential equation. Okay, so we'll take all three of these guys and put them in. All right, so I'm going to do my best to kind of keep this neat and orderly, but yeah, you know how this happens with me. Okay, so I'm going to group everything by like U1s and U1 primes and U2s, U2 primes, things like that. So we're going to start with the Y double prime. So we're going to get, hold on a second here. U1 prime, Y1 prime, plus U1, Y1 double prime, plus U2 prime, Y2 prime, plus U2, Y2 double prime. Now, for the Y prime, I'm going to multiply that by P. So I'm going to get U1 times P times Y1 prime. And then I'm going to get P times U2 times Y2 prime. Okay, so that was that times the P. And then I'm going to get Q times my original. So U1 times Q times Y1. And then U2 times Q times Y2. And all that stuff's being added. And that needs to equal G of T. So I've got U1 prime, Y1 prime, plus, all right, so let's look at all of this. If I factor out the U1, notice what I've got is Y1 double prime plus P times Y1 prime plus Q times Y1. And all of that stuff in the parentheses is 0. Because Y1 was in the fundamental set, which means when I plug it into this, I get 0. That's what that says. So all of that is gone. I have a U2 prime, Y2 prime. And then again, let's factor out our U2. And I apologize, I'm running out of space. But by the exact same argument, that's also equal to 0. So this thing reduces then to Y1 prime or U1 prime plus U2 prime Y2 prime equals G of T. So again, let me highlight the restriction. And then this restriction. And again, there's our system of equations. And we can rewrite it as a matrix. And if you look at this, that's exactly what we saw. You can see the Wronskian. And then it's equal to 0 G of T. Well, ours was 0, 3 cosecant of T. Okay. So it turns out that, yeah, we're going to solve any of these in exactly the same way. And here's what I find really beautiful. Notice that none of this, in terms of finding the actual solution, has anything to do with P and Q. I don't care at all what these things look like, other than the fact that they determine my fundamental set. But if I know my fundamental set, good enough. So it's actually a very robust method. Like, it works for just about anything. However, you can imagine that the integrals here get kind of gnarly, just depending on what they look like. Now, let's kind of continue. Since it's a 2x2 matrix, we can actually find its inverse. I don't know if you remember, but finding an inverse of a 2x2 is pretty easy. So let me just remind you. When you had a 2x2 matrix, call that guy A. A inverse, it was equal to 1 over the determinant of A times dA negative C negative B. Is that right? Hold on a second. No, that's not right. I'm trying to remember the shortcut, and I don't even remember the shortcut. I think those you just changed the sign. I think that's just negative.
Yeah, I think you just changed the signs on
Negative
those ones.
C. So AD minus BC minus B. Yep. Okay, so this is in general what you do. Okay, well, remember that this is the Wronskian matrix. So if we go with this guy, capital W being y1, y2, y1 prime, y2 prime. Okay, the determinant of this is the Wronskian. So we're going to have 1 over the Wronskian times y2 prime, y1, negative y2, negative y1 prime. So there's our inverse. Now, think about what we're doing is we're multiplying that to 0 g of t. So the first entries don't matter because they're going to get multiplied by 0. So what we get is u1 prime is equal to 1 over the Wronskian times minus y2 times g of t. And then u2 prime, same deal. It's going to be 1 over the Wronskian times y1 times g of t. So we're almost done, actually, in terms of doing this generically. Because the last step now, since those are u1 prime and u2 prime, here's where we end. We know that u1 is going to be the negative integral of y2 times g over the Wronskian. And then u2 is going to be the positive integral of y1 times g of t over the Wronskian. And that's what we should put the box around. Because there's your generic variation of parameters. So it doesn't matter at all. If you know y1 and y2, but that's a big if, right? You got to know the entire fundamental set of solutions to the homogeneous. But if you have them, here is a way that you can find the integrating factors to build your particular solution, right? Because y particular was u1 times y1 plus u2 times y2. I should probably include that in the box. All right, so good news. I was going to say good news, bad news. Only bad news is this is just, it's long and tedious, but by this point, yeah, that's what differential equations is. So how about, let's just go to the good news. The good news is we've already done now all the work for any one of these ever. All we have to do is find our fundamental set, make the Wronskian, and plug it into those formulas. I know it doesn't feel like good news at this point, but it is. It's definitely good news because we're in a place where we can solve anything like this. Again, though, we need to know what our fundamental set is. All right, so there you go. There is the method of variation of parameters. I don't think I actually wrote that down anywhere. Hold on a second. I think we just kind of dove in, and but this is called variation of parameters. All right, so that's what this method is called, and it works. It even would work for things when we used undetermined coefficients. If we wanted to, we could have done it exactly this way. Depending on how you feel about solving systems, this actually may be faster, right? For example, like let's say we had y prime or y double prime minus 2y prime minus 3y equals cosine of t. So we did that one with undetermined coefficients. But let me show you how we could use variation of parameters to get it. And this might actually be faster. We'll see. Okay, so start by finding your homogeneous. So we get e to the 3t, e to the minus t. So that's y1 and y2. You can actually label them whichever way you want. It doesn't really matter. Okay, so let's build our Wronskian matrix. So there's our Wronskian. Again, we just put in y1 and y2 and then take their derivatives. So the determinant of that, because we definitely need the determinant, is minus 4 e to the 2t. All right, so let's plug it into variation of parameters. So u1 is going to equal negative integral of y2 e to the minus t times g cosine of t divided by the Wronskian. So u1 is 1/4 the integral of e to the minus 3t cosine of t. I'm definitely way too lazy to do that at this point. So let me just do it with the calculator. So e to the minus 3 times the cosine. Okay, so I get e to the minus 3t times sine t over 10 minus 3 cosine of t over 10. All right, so that's u1. Okay, so u2, similar. We're going to integrate y1, which is e to the 3t, times g, times cosine, divided by the Wronskian, minus 4 e to the 2t. So if we simplify that just very little bit, this is minus 1/4 integral of e to the t cosine of t. All right, and what I get there, minus 1/4 minus 1/8 e to the t times cosine t plus sine t. All right, so our y particular then is going to equal this thing times y1. So the e to 3t and e to the minus 3t cancel. So I'm left with 1/40 sine of t minus 3/40 cosine of t plus u2 times y2. Well, the e to the minus t cancels with that. So I get minus 1/8 cosine of t minus 1/8 sine of t. And I think that becomes 1/8 sine of t minus 1/5 cosine of t, which should be what you get if you did undetermined coefficients, because we would have made a guess of the form a cosine plus b sine, and it should lead us here. So is this better? Is this faster? Is it easier? I don't know. Depends who you are. But this is a method that will work always, as opposed to undetermined coefficients, which only works when it's a nice form. Whew. All right, well, there you go. Variation of parameters. So just like all the rest of these, this is going to get easier the more of it you do. The more of them you practice, the easier this is going to come. But now we are integrating. So remember when Bradley earlier was like, it's kind of cool how in this section we don't have to integrate. Right, but in general you do. And that happens both with this variation of parameters and reduction of order that we saw last time. All right, so there you go. Any questions on this guy? Do you even know where to start with questions at this point? Is your mind completely numb? All right, well, then I think we're going to go ahead and call it a day. Your brain is probably sufficiently mushed. But just practice this, look at it again, and you'll see that it's not terrible. It's just a matter of getting it set up right. All right, so with that, I'm going to go ahead and stop the recording. Just want to remind you there is homework due tonight, so don't forget to get that done. But other than that, have an awesome couple days, and I'll see you all on Wednesday.